Question E3. This question is about cosmology. And A. State how the observed redshift of many galaxies is explained. Now, this idea of redshifting is that the source of that light from distant galaxies and so forth is moving away, and when it moves away, the spectrum of light that comes to us on Earth is actually redshifted. The wavelength is actually increased, and therefore it looks like it's been moved towards the red side of the spectrum. So why is this? Well, it's basically because we feel that the universe is expanding, and therefore most galaxies, or most stars outside our galaxy, most galaxies are moving away from us, moving away. Okay. B. Explain how the cosmic microwave background, CMB, radiation is consistent with the Big Bang model. Now, this microwave background radiation comes from the idea that at the start of the universe there was a Big Bang, or this massive, you could call it an explosion. So it started the universe with the explosion of some sort, where we had space expanding at a rapid rate, and this initial energy, the initial energy was very high frequency, low wavelength radiation. And what's happened is, as the universe has expanded, we have that this radiation has redshifted. So the radiation has redshifted or expanded. Okay, it's so we have that. It's presently, when we put it into Wien's formula over here, the present temperature that we get when we put the present background radiation to that, we get a temperature of about 2.7 Kelvin comes out, which is also consistent with what we would expect from the universe, from starting from that high energy to the low energy that we have in our cosmic background radiation. Question C. Calculate the temperature of the universe when the peak wavelength of the CMB, cosmic microwave background radiation, equals the wavelength of red light 7 times 10 to the negative 7. So we would put that into here, into this formula over here. So we're going to have here that lambda max is equal to 2.9 times 10 to the negative 3 over the temperature. So temperature is going to equal 2.9 times 10 to the negative 3 divided by 7 times 10 to the negative 7, and we would get about 4,100 Kelvin. So that would have been the temperature of the background radiation at that time, obviously very high in comparison to what it is now.